Hello, welcome back to another one of my videos. Unfortunately, I'm gone. But today, we're going to go over a little bit about what I showed you guys last time when I did that super long proof of the fundamental theorem of calculus. I just want to go over those ideas again because it's just an amazing, mind-blowing piece of mathematics. And then we're going to get into what is called in the textbook, chapter 4.1, so that will be kind of down here. And that's going to be stuff dealing with, we could call this anti-differentiation, which is a very related idea to the fundamental theorem. It does have some stuff about differential equations, but for now, you guys just ignore the differential equation aspect. I might just mention those terms, but really I'm going to be focused on just doing anti-differentiation or doing indefinite integrals. You'll know what those terms mean later. But for now, let's look back at the fundamental theorem of calculus. It says that if f of x is continuous on this closed interval from a to b, where a and b are constants, and suppose f of x is a differentiable function, that it has sort of this partner function, capital F of x, such that if you take the derivative of capital F of x, right, maybe another way we could write it is like this. If you take the derivative of this other function, it is equal to lowercase f of x. So lowercase, capital F, totally different functions, right, but they're related through the derivative. Then what this says is that the definite integral, right, that's a definite integral of lowercase f of x equals capital F of b minus capital F of a. And man, that's an amazing statement. It's an amazing statement because remember what this is. It is a limit of a Riemann sum of, it's something like this. And you got n going to infinity, and there's an n up here, and I equals 1. That's the definition of a definite integral. So you're adding up all these rectangles, and you can imagine you have like a million rectangles, or a trillion, or a billion. But somehow this crazy calculation can actually be simplified into finding the output of a function here, finding the output of the function here, and then just subtracting the two. It just boils down to subtraction. This amazingly complicated sum area under a curve can be calculated using subtraction. Absolutely mind-blowing. Now, some terms, though, that we didn't really go over when I proved this to you, or I probably didn't mention them, is we call any function f of x, capital F of x, that satisfies capital F prime of x equals lowercase f of x, an antiderivative. And we call it that for good reason. It's literally the opposite of taking a derivative of f of x, right? So just to give you an example, right, if f of x equals 3x squared, we can very well naturally ask, okay, the derivative of what thing is going to result in 3x squared, right? The derivative of what thing is going to result W2. The derivative of what thing is going to result in 3x squared. And so it's kind of like, so we can very easily do this one, right? We could say, okay, maybe capital F of x equals, not 3, x cubed. Hooray, we did it. We found the antiderivative. But hang on, some of you guys are thinking, well, that's not the only answer, is it? Because couldn't I also take the derivative of x cubed plus, I don't know, 7? Like the number 7? Wouldn't that also give me 3x squared? And you're right, it would. So actually, this x cubed, that's an antiderivative, and so is this. And so is, let's use one of my favorite numbers, x cubed plus 64, right? That would also give you 3x squared. That is also considered an antiderivative. So think about this carefully. The derivative of any function is always going to be the same no matter how many times you do it. But the antiderivative of any given function could be one of many functions, right? So if you think of this using sort of function map, sort of pictorial ways of showing this, right? X cubed plus 7, x cubed plus 64, right? We could even subtract a number. Doesn't really matter what the number is. As far as differentiation is concerned, all of these, right? If we're talking about the derivative, taking the derivative, all of these turn into 3x squared. So one question we could ask is, okay, if the integral is the opposite of, right, if this is the integral, if it's the opposite of differentiation, which one is it going to take us to, right? It's a very good question. How do we know? Well, the answer is we actually don't know. And it's okay that we don't know. So this is where the idea of the indefinite integral comes into play, right? So the indefinite integral is written this way with a big S. So we would say the indefinite integral of 3x squared dx equals. Notice how we don't have any bounds, right? There is no a to b. This is indefinite, right? The definite integral has two numbers. It gives you a clear boundary marker for the area you're trying to create under the graph. Here we do not have bounds. We're not really thinking as much about areas. We're thinking more in terms of antiderivatives. And what we would say the answer is that the indefinite integral of 3x squared dx equals x cubed plus some constant c. That constant c is typically called the constant of integration. Right? Because like we showed before up here, there is actually an infinite family of functions that all have the derivative 3x squared. And we want to represent that entire family on the right side of this equation. So this is a family of functions. So even though there are infinitely many of them, they are all functions with x cubed. So they're all cubic polynomials. The only difference is that they're translated. So one way to see that is imagine, right, here's the graph of, right, x cubed. So this is x cubed. Oh, in fact, you know what? I shouldn't draw the x or y axis. All right, so let's just suppose that's x cubed. If I were to take this exact graph using the magic of notability here, and I just shift it up a little bit, right? Let's say by 2 units, x cubed plus 2, and I look at the derivative at any x coordinate on both of these functions, right? So if I have the x-axis here and here, and let's say I choose the x-coordinate, let's just say 1, 2, 3. That's probably not right. Let's see. Let's make this a little bit more accurate here. I believe I have to draw the x-axis around here for this to be more accurate. So something like this, right? So if I were to look at, let's just use the x-coordinate 2, right? What is the derivative at 2? Remember what the derivative is. It's the slope of the tangent line. So we'd get a tangent line like this. But also notice, because x cubed plus 2 is just a shifted up version, the slope of this tangent line should be identical. Right now it isn't, because I'm probably not very good at doing that vertical translation. But the idea is all tangent lines at any given x value should be the same. It should be the same. And that's why we have an infinite family of functions for our indefinite integral. So that's some really important vocabulary: constant of integration, family of functions, indefinite integral. Cool. Another way we can phrase this, which we will do a lot more later on, is through differential equations. So we could say that, let's see, I guess we would say that x cubed plus c is what we would call the general solution to the differential equation capital F prime of x equals 3x squared. So this is what we would call a differential equation. It's an equation where, unlike in algebra, you're trying to solve for x. A differential equation, you're trying to solve for a function. What function, when you take the derivative, gives you 3x squared? Notice how similar this is to what we're doing over there anyway. That's going to come in later, right? So don't worry about this part as much for now, but maybe I'll just leave it up there. Okay, let's actually get down to some practice, though. So here we have the integral of cosine of x. Indefinite integral. What is this equal to? Well, we know, well, again, it's kind of like asking the derivative of what equals cosine of x. Well, we know what derivative gives us, or what function has the derivative cosine of x. It's on your green sheet, right? That's sine of x. So that's actually the answer to the integral over here. The integral of cosine of x is sine of x plus c. You have to have this, right? Do not leave off your plus c if you're dealing with an indefinite integral. You have to have that constant of integration so that you're representing the entire family here. If I have the indefinite integral of, let's say, let's do sine of x, right? Sine of x dx. Well, again, think of it this way over here. The derivative of what gives me sine of x? Well, it's actually not cosine. Not cosine just by itself. It's actually negative cosine of x, right? Because the derivative of cosine is negative sine. To get rid of that negative, we would have to make this one negative, so that we end up with positive sine. So the antiderivative, or the integral here, would be negative cosine of x plus c. Let's see, what about the integral of x? Let me go ahead and raise it to the power n, where n is just some number. It's a constant, right? You always have to have this dx at the end, by the way. It's integral notation. So we got to think, the derivative of what equals x to a power? Right. Think of the power rule, right? So one way we could do this is we could say, okay, if I have a constant times x to the b, right? What do these two guys need to, what numbers or expressions do they need to be so that the derivative turns into that x to the n? Well, what we could do is we could work with them as constants, right? Remember, the power rule says the b comes down, multiplies with the a, get a times b times x, and then we subtract 1 off of b. So we would have b minus 1. Okay, so let's think about it, right? In order for this to be equal to n, what does b have to be? B would have to be n plus 1. Okay? If b is n plus 1, and we need to have a coefficient of 1, what does a need to be? Well, a needs to be 1 over n plus 1, right? If a times b gives you 1, then a must be the reciprocal of b. So what is this saying? Let me just get rid of all this junk. You can rewind if I'm going too fast. This is saying that there's a formula here for the antiderivative, that if you have the integral of x to the n, then the antiderivative is x to the n plus 1 over n plus 1. Nice. So that's what goes over here. X to the n plus 1 over n plus 1 plus c, right? And you can even test this out pretty easily, right? If you take the derivative of, I don't know, x to the 7 plus 1 over 7 plus 1. Oh yeah, that's just the derivative of x to the 8 over 8. And that's just x to the 7. Oh, look at that, right? That matches perfectly with what we have there. So this is kind of like, one way we could think of this is almost like the anti-power rule. Remember, the power rule had us multiply by the power. Here we're dividing by the new power. And instead of subtracting 1 off the power, we're adding 1 to it. So it's kind of doing the opposite of what we normally do with the power rule. It's doing everything in reverse. All right, cool. So that's an interesting example. Let's do maybe another one. The integral of e to the, I'll use a number here, maybe 3x, right, dx. Now, when we take the derivative of this thing, we normally get 3 times e to the 3x, but this is the integral. So you can probably guess what's going to happen, right? The derivative of what gives me e to the 3x? Okay, so in this case, if you think about it, I should be dividing by 3, right? So that when the derivative acts on this thing, the 3's go away. That's the whole point. It's the opposite. It's the antiderivative. And that's what the integral is doing. It's doing the antiderivative. So over here, the answer would be e to the 3x over 3 plus c, right? These would literally be our answers. All these, yes. You would leave c in your answer, yes. These are not numerical. Not going to get a number answer here. We have a family of functions as our answer. Okay, cool. Let's see. Let's do some other examples that are a bit trickier, a little bit more concrete. So let's do the integral of x plus 1 over the square root of x dx. Right. Well, if you play this game that we did up here, it's actually going to be pretty tricky to do that because it's not super obvious what function, if I take the derivative, gives me this thing. It's not obvious. But just like with the derivative and the limit and the Riemann sums that we've been doing, we can manipulate what's here before we actually apply the integral, right? So one thing we might want to do is actually just divide through by the square root of x and just see where it goes. So here we have x over the square root of x plus 1 over the square root of x dx. And notice how we can simplify some stuff, right? So we get, looks like the square root of x plus, now this is, well, I'll just keep it as 1 over square root of x for now, right? And Notice how this formula is just in terms of the power as a number. So let's go ahead and turn these into x to the power of something. Right? This would be x to the power of 1/2 plus x to the power of negative 1/2. Cool. A nice property of the integral that we can do is we can actually split it up if we really want to, right? We could actually split it up into two integrals if doing the whole thing is too confusing for you. All right, so we can do this. We'll get into that more with the next section. But if we have it written this way, we actually have a nice little formula right here, right? So if n is 1/2, then this thing turns into 3/2, and so does this. So we know what this integral becomes. It becomes x to the 3/2 over 3/2, right? This is all in the denominator here, plus some number c. All right, now let's do the next one. If n is negative 1/2, then add 1 to it. All right, so we get x to the positive 1/2 now, divided by positive 1/2 plus c. All right, so we're here, and we can actually put some things together and we can simplify some things, right? So this x to the 3/2 power, this division by 3/2 turns into 2/3 x to the 3/2. We can actually just leave it like that. We can also simplify this guy, right? So this would turn into 2, right? Dividing by 1/2, 2 times x to the 1/2. You can leave it like that if you want to. Now these two constants, we don't know what either of them are, but in fact they don't really represent one particular number. They just represent all constant numbers. And if you take a constant plus any constant, what you end up with is just a constant. And so we would say that this is the antiderivative. In fact, if you just did the integral here, just directly, you would actually just get something like that. So the idea is that these constants of integration, they just represent numbers that we don't know. And if you add numbers that you don't know, you just end up with a number that you don't know. So don't overthink it too much, right? Those c's combine. Let's do some more. So the integral of 2 over the square root of x dx. Let's see, let's rewrite that. This is going to be 2 times x to the negative 1/2 power dx. And what does this turn into? Well, it's not quite like our little formula up here, right? Because we have a coefficient right there. You can still try to just figure it out with the coefficient, or you can actually, this will be a property we'll go over later. You can pull the 2 out if you really want to. Right? We could just turn this into x to the negative 1/2 power. And we know how to do that, right? Now, if you pull the 2 out like we did, right, this will be 2 times whatever the answer to that integral is. That's going to go there. And the answer to the integral is x to the 1/2 divided by 1/2 plus c. Now at the end, we're going to have to distribute the 2 back in, which is pretty easy. And notice how this dividing by 1/2 turns into another 2. So we get 2 times 2 is 4, x to the 1/2. And then the 2 times the c just turns into an integration constant, right? 2 times a number we don't know is just another number we don't know, right? So it's just c. All right, let's do another one. Let's do t squared plus 1 squared dt. Now in this case, we don't really have to rewrite powers, but it's not really clear what the antiderivative of that is. And so what we want to do is let's actually just go ahead and multiply this out, right? This is just another way to write it. Okay, let's distribute it all out, right? You have to actually multiply all of this. you end up with t to the fourth plus, we get t squared plus another t squared, that's 2t squared, and then plus 1 times 1, so plus 1 dt. And then, now we just find the antiderivative of each of these terms, right? And then we just add a plus c at the end. So t to the fourth turns into t to the fifth over 5 plus, now 2t squared, if you think about it, this should turn into 2t cubed over 3, right? If you don't believe me, just take the derivative, right? The derivative should take you back to 2t squared. And then the 1, it's just going to be t, right? The derivative of t is 1. There we go. There's our antiderivative. Let's maybe try to do 2 more. Right, we're kind of going speed round. I don't want to waste y'all's time here. X cubed plus 3 over x squared dx. Okay, how can we reduce this? Let's just divide through by x squared. Right, this gives us the integral of x plus 3 over x squared dx. We can actually rewrite this term. Maybe we go ahead and do that. Right, so we have x plus 3 times x to the negative 2 dx. And now let's just do the antiderivative of each term. So antiderivative of x, that would be x squared over 2, right? So that one's pretty straightforward. What about the second one? Again, you want to think backwards, right? So we're adding 1 to the negative 2, and then we're going to divide this term by that new power, right? So think very carefully. Can you see it? It's going to be 3x to the negative 1 divided by negative 1. I know that seems like it shouldn't work, but it actually does. It actually does. And then, of course, we have integration constant c. And like I always tell you guys, you should simplify that, right? So what does this turn into? Let me write the first term a little differently. I like this way of writing it better. So 1/2 x squared, this will turn into minus 3 over x, right? This is a much more proper way to write your answer. And yes, I would take points off if you left your answer like that. This is good, this is bad, right? Okay, let's do another one. Maybe another slightly harder one. This is the cube root of x times x minus 4 dx. Okay, again, antiderivative is not super clear. How about we manipulate this? How about we maybe distribute this stuff, right? Now you got to remember, what is this? This is x to the 1/3 power, right? So as you distribute, you should know what the terms look like. The first term turns into x to the 1/3 times x to the 1. That should be x to the 4/3, right? On the second distribution, that's pretty easy. Minus 4 times x to the 1/3. Okay, let's do the antiderivative now, right? So x to the 4/3, again, use the formula, the anti-power rule. Take this power, add a 1 to it, and then divide by the new power, right? So 4/3 plus a 1, well, plus 1 is like plus 3/3, right? So 4/3 plus 3/3 equals 7/3. So this will be x to the 7/3 divided by 7/3. I know this is kind of a weird way to write fractions, but this is the way I do it. Make sure you put parentheses so that you know this is the true denominator, right? If you do it this way. And then up there, right, 1/3 plus 1 gives you 4/3, and then we divide by 4/3. So we end up with minus 4 times x to the 4/3 divided by 4/3, right? And here comes the part that always kills you guys. simplifying. Algebra. How do we simplify this, right? Well, dividing by 7/3 is the same as multiplying by 3 out of 7. And this is times x to the 7/3. In this case, 4 divided by 4/3, the 4's cancel, right? Now we're just dividing by 1/3. That's going to be minus 3 times x to the 4/3 plus c. All right. Now let's do one last little challenge problem, and then I'll let you guys go. Feel free to rewind and look back at these examples if you didn't understand what I was doing. Let's do the integral of, this is going to be a tricky one, 4 cosine of 3x dx. So we got to think, right? The derivative of what would give me this? That's what we got to think. So the derivative of what function gives me cosine? Well, I know that it's going to be sine. And specifically, right, to give me cosine of 3x, this would have to be sine of 3x as well, right? That 3 doesn't just come from nowhere. It should have been there originally in the antiderivative for it to show up over there. So if we know that a 3x has to be there, the million-dollar question is, what should be the coefficient so that when I take the derivative, I end up with 4? Right? Because remember the chain rule, right? In fact, maybe we do it this way. Maybe we say, we don't know what this number is. We could call it a. And we could say we want the derivative of a sine of 3x. I want this to be equal to 4 cosine of 3x, right? That's my goal. Now, if I just do this derivative, I know how to do that, right? If a is a constant, I know that the chain rule is going to happen, right? So if you know your chain rule, that's going to be a cosine of 3x times 3. And that should be equal to 4 cosine of 3x. Now notice we have a cosine of 3x and a cosine of 3x on each side. And if that's not 0, we can actually divide it out on each side of the equation. And all we're left with is 3 times a equals 4. So this mystery constant needs to be 4/3. And that actually should make a lot of sense, right? So 4/3. And then, of course, a plus c. Because notice how when we took the derivative, right, from here to here, we ended up multiplying by 3. Whereas when we took the integral from here to here, we divided by a 3, right? They're the opposite of each other. So the derivative and the integral, right? If this is capital F of x and this is lowercase f of x, the derivative takes you this way. The indefinite integral kind of takes you the other way, right? But of course, you have to add that plus c, right? So anyway, I hope this helped. There will be some homework posted. This is from 4.1 in the textbook. And good luck, guys.